Welcome back to the Deep Dive. Today we are really tearing down a fundamental illusion of the modern world.
Yeah.
For years we've talked about the cloud as if it were this invisible, weightless and infinite thing just floating out there in the ether.
That illusion is completely collapsing.
Yeah.
As we train and deploy artificial intelligence at this incredible new scale, as we build the infrastructure for these global large language models, the ether is being replaced by tons of concrete.
Right.
By intricate cooling towers and an absolutely insatiable, quantifiable thirst for electricity. The digital revolution has, it's physically anchored itself to the power grid.
It's a massive, almost counterintuitive shift, and the central, surprising concept we're unpacking today is exactly that. The most strategic resource in the AI revolution is no longer a speedy chip or a clever algorithm. It is the gigawatt. We're going deep into the physical constraints, the power, the heat, the water, that are now defining the future of AI. Our deep dive mission is to understand how the focus has moved, really, from software ingenuity to hard physical infrastructure.
And our core source for this, the battle for the gigawatt, silicon and the thirst for energy, makes it incredibly clear that the real war for AI supremacy is now being fought at the substation.
This is such a crucial conversation. It affects everything from climate policy to national security, and we really want you to be part of it. Before we jump in, if you find this kind of in-depth analysis valuable, please consider supporting us.
It makes a huge difference.
It really does. Take a moment to subscribe right now, hit that like button, and maybe share this deep dive with any colleagues working in energy policy or tech. And also, let us know in the comments, what do you think is the biggest bottleneck right now? Power, water, or land?
I'd be curious to see what people think.
Okay, so let's unpack this central idea. For nearly a decade, the tech world was obsessed with scarcity. It was all about the chip shortage, right?
Specifically NVIDIA's GPUs, yeah.
We focused on silicon as the hard limit. The thinking was, if you can make more silicon, you can scale. What has fundamentally changed?
The change is that there's a new constraint, one that is far, far more difficult to solve than just manufacturing chips, and that's power capacity. While chips are still crucial, obviously the industry has gotten very good at building fabs and accelerating silicon production. You can increase the rate of chip output, but
if you can't just print more electricity.
Exactly. Manufacturing electricity and the massive, expensive, high-voltage transmission lines you need to carry that power is difficult. It's slow, and it faces enormous regulatory and, geographical challenges.
So the bottleneck has literally shifted from the component to the socket on the wall. Instead of waiting 6 months for a GPU from Asia, companies are now waiting years for a utility company to approve and build a new substation.
That's it, precisely. The supply chain problem has moved from microelectronics to macro infrastructure, and that's why the sources highlight this new real estate game. It has nothing to do with fancy buildings or urban centers anymore. Tech giants are aggressively hunting for undeveloped land that just so happens to have an existing high-capacity grid connection. That connection is the single most valuable piece of real estate in the AI world today.
And the scale we're talking about here is, frankly, a little terrifying. We're not talking about just upgrading a server rack.
Oh, no.
These are demands that are stressing the stability of entire regional grids.
We truly are. We've rapidly moved from what we used to think were large data centers, maybe 20 megawatts just a few years ago, to planning what they call gigawatt scale campuses.
A gigawatt. Just put that in perspective for us.
Okay, so 1 gigawatt of power can roughly supply every single home in a mid-sized city, maybe 750,000 households.
Wow.
A single modern AI training cluster, especially during the heavy training phase of a new model, consumes the energy equivalent of that entire city 24/7.
And it's a constant draw, isn't it? It's not like it peaks in the evening.
It's an incredibly rigid, demanding load that, frankly, very few existing grids were ever designed to handle.
Which immediately raises the question of grid fragility. If these major AI players are suddenly sucking down that much dedicated power, aren't they competing directly with the cities and industries right next door?
They absolutely are. And this is where that political tension starts to build, especially in North America and Europe. When demand surges this fast, the only way to meet it is often to ramp up existing power sources, which can mean older, higher carbon facilities.
Or you risk brownouts elsewhere.
The speed of AI scaling is just completely outpacing the speed of grid modernization.
Okay, let's say you solve the power problem, you secure the gigawatt. But what about all the waste heat that electricity generates?
This is where it gets into pure physics. And it's the second major barrier. The thermal limit. People think data centers, they think wires, they don't think about millions of gallons of water.
So why are these silicon brains so thirsty?
It's because high-performance GPUs run incredibly hot. I mean, a modern chip generates a heat flux that's comparable to a nuclear reactor core just packed into this tiny, tiny area.
And if they overheat, they just fail.
They fail, or they throttle their performance way down. So to stop these chips from basically melting themselves, you need sophisticated industrial-scale cooling.
Which often relies on a surprisingly simple process: evaporative cooling.
Precisely. A lot of facilities use these huge evaporative cooling towers. They spray water into the warm exhaust air, and that evaporation process sheds heat really efficiently. It's like a giant industrial swamp cooler.
But at the gigawatt scale.
At the gigawatt scale, that water consumption just explodes. These places need millions of gallons of water every single day, and it's consumed, it's not recycled, it's literally turned into steam and lost to the atmosphere.
That just immediately grounds this abstract digital world in a very, very real physical problem, especially in climate-stressed regions, the American Southwest, parts of Europe facing drought.
It creates a direct, tangible conflict. The sources call it a socioeconomic tension. If a data center in, say, Arizona is using evaporative cooling, its water use creates a measurable strain on local reservoirs.
So the needs of the AI are suddenly at odds with the needs of the local population.
For drinking water, and just as critically, for agriculture. We are already seeing cities push back, putting moratoriums on new data center construction specifically because of the water demand.
That's a powerful point. We've hit a physical wall. The source material mentions the thermal limit. Does that mean the density of chips we can use is just capped by our cooling tech?
That is exactly right. The industry is now limited not by how small they can etch transistors on silicon, but by the physics of heat transfer. How much heat can you physically pull out of that room before the chips start to fail?
So what's the solution there?
Well, it's forcing innovation into extreme methods like liquid immersion cooling, where entire servers are literally dunked into vats of specialized dielectric fluid.
Which sounds incredibly expensive and complex.
It is, but it's becoming necessary. This constraint means even if chip production tripled tomorrow, the lack of cooling infrastructure, the custom racks, the fluids, the massive chillers, that would be the new bottleneck. The thermal limit is the real ceiling on AI growth right now.
So if power and cooling are the dominant constraints, let's zoom out. What does this economy of scarcity mean for the global economy? This chase for the gigawatt is reshaping geopolitics.
It is, and if we look at the global context, you see this fascinating historical parallel. Just like the early industrial revolutions saw factories clustering around coal mines or later oil fields.
But you go where the energy is.
You go where the energy is. AI infrastructure is now migrating toward regions with cheap, stable, and abundant energy. The sources label this geopolitical energy arbitrage. The number one business decision isn't where's the talent, it's where are the electrons cheapest and most reliable.
Not just cheap land, cheap, reliable electrons, 204/7. And the sources point to a really surprising alliance being formed to get them: big tech and nuclear power.
Indeed. We're seeing major tech players, Microsoft, Amazon, and others, striking aggressive deals to either restart dormant nuclear reactors or invest heavily in developing small modular reactors, SMRs.
For our listeners who might not be familiar, can you quickly break down why SMRs are the focus instead of huge traditional nuclear plants?
Sure. Traditional nuclear is massive. It takes decades to build, huge regulatory hurdles. SMRs are smaller, often factory-built and modular, so they're quicker to deploy, easier to scale, and they have inherently safer, simpler designs.
They sound perfect for a tech company.
They're the perfect solution for a company that needs, say, 500 megawatts of dedicated power right now without that multi-decade commitment of a full-scale plant.
But isn't relying on nuclear just shifting the political headache? I mean, nuclear has always been politically volatile, expensive up front.
That's the calculation they're making. The strategic value of nuclear outweighs that political complexity, mainly because of its stability.
It's always on.
It is always on. It ensures a 247 power supply that doesn't fluctuate with the weather or the sun or the wind. For a tech giant making these multi-billion-dollar investments, securing a guaranteed carbon-free power source gives them a massive long-term competitive edge. Stability equals performance, and that equals profitability in the AI race.
And this leads directly to a huge national implication. Energy sovereignty is becoming indistinguishable from technological sovereignty.
That is the most profound takeaway from all of this. Nations are realizing that their ability to compete in the AI age is directly tied to the strength of their electrical grid. If a country can't provide the gigawatts for its own domestic AI factories,
Its industry has to go elsewhere.
its local tech industry is forced to outsource its most fundamental computing needs. They have to rent intelligence from another nation.
And what does that really mean to rent intelligence?
It means higher costs, for one. But more critically, it means a loss of control over the models, the data, the pace of your own innovation. If your core computing power is hosted in another country and their grid fails, or they decide to raise prices or even restrict access for geopolitical reasons, your whole industry is vulnerable.
You're ceding control.
You're effectively ceding control over your digital future.
Yeah.
This is why governments are suddenly treating grid upgrades as a matter of national security.
Which brings us to this profound irony that the sources highlight. AI is so often talked about as the ultimate tool to solve the climate crisis, right?
Absolutely.
Optimizing our grids, discovering new battery materials, forecasting climate systems.
And that is the promise, you know? The long-term efficiency gains that AI could bring are potentially revolutionary. But we have to balance that optimism with the short-term reality of the resource drain.
How significant is that short-term drain?
Oh, it's incredibly significant. We have to separate training from inference. Training a large model is this one-time massive energy burst. It can consume the power of thousands of homes for months.
And then there's inference.
Then there's inference, which is the daily use, like asking a chatbot a question. It's lower energy per query, but it happens billions of times a day. The combined effect is driving a massive surge in carbon emissions and resource consumption right now. Some studies suggest AI's electricity demand could soon rival that of a small country.
So we're caught in this central tension. The machine designed to help us solve the climate crisis is, in the short term, accelerating it, a huge paradox.
Exactly. The industry is in a monumental race against time. Can AI become smart enough to solve the energy problem, by improving fusion, optimizing renewables, creating new efficiencies, before its own explosive energy use makes the global challenge significantly worse? That is the defining tension of the next decade in tech.
This dive into the battle for the gigawatt just offers such a clear lesson. We've moved away from that early promise of digital abundance, that weightless cloud. And we are back in a world defined by the most concrete physical constraints imaginable. Concrete foundations, millions of gallons of water, and raw megawatts of power.
The key shift is realizing that intelligence, even artificial intelligence, needs a heavy physical anchor in the real world. In this new economy of scarcity, the winners won't just have the best code. Success will be defined by those who can secure the energy to run it all. The source material says it brilliantly. Leadership will be defined by those who control the enchufe, the plug, as much as the software.
That's fascinating. So what's a final provocative thought we can leave our listeners with, building on this idea of physical constraints?
I'd say reflect on this. If vast, stable energy is now the primary driver, how will the physical location of that energy scarcity redraw the map of tech innovation? Instead of Silicon Valleys being near universities and venture capital, will the next hubs of innovation be built next to hydroelectric dams or geothermal fields or maybe dormant nuclear facilities? That geographic link to power is going to fundamentally change where true technological power actually resides.
A huge thank you for joining us on this deep dive into the real-world constraints of the AI revolution. If you found this conversation insightful, and if you have colleagues focused on the future of energy or data center strategy, please share this deep dive with them.
And we absolutely want to hear your perspective and keep the conversation going. If you have more questions on nuclear power's role or the challenges of cooling, drop a comment below. And if you haven't yet, please hit that subscribe button and give us a like so you don't miss our next deep dive.
Thank you for listening, and we'll catch you next time.